Okay, welcome back. In this example, we are going to be going over a poster problem. The problem says that you are designing a poster that should contain 50 inches squared of print. I should probably change my color so it stands out a little more. And it also says that your paper, so 50 inches square of print, is going to have a 4-inch margin at the top and bottom and a 2-inch margin at each side. What will be the overall dimensions that will minimize the amount of paper used? Okay, so minimizing paper used. Again, we're talking about minimizing the area of that poster. So I'll just write that down so I have that in mind. And I need to give the dimensions that's going to accomplish that. Well, what I did is I just kind of put some rectangles here to showcase my poster. Imagine this is the big poster, but I'm only allowed to print on 50 inches squared. So this white stuff represents kind of the print area. It's similar to when you print on a Word document. You don't print on the entire page. There's just certain area where you're allowed to print. And so we have to make sure that we have 4 inches on the top and 4 inches on the bottom, 2 inches on the side, and 2 inches on the other side. And so, again, since we're minimizing the area, we're going to need some variables. And there's a couple ways to do this. I can either let the inside be x, the print of the area be x, so that would be from kind of where the white corners start and end, or I could let the outside be x. Either way it works. One of them is a little bit more difficult algebraically than the other. I believe that if you let the inside be x, it ends up being a little bit easier. So if this inside piece is x, and then you can see to get from this end to this end, we're going to add 2 inches each side. So really the outside of the poster should be running us x plus 4. If we go y for the other one, so let's call this one y. You know that's y, again, represents just the white print stuff. So it's going to be from the top all the way to the bottom. We got to add those 4 inches, so this is actually be y plus 8. Okay? And since we're minimizing the area of just a rectangle, the area of a rectangle is base times height or length times width. So we're going to use this x plus 4 and this y plus 8, making sure to use parentheses so that we multiply all the terms together. Again, this is just the area equation, but I have the issue of having 2 variables. I'm not allowed to do that. So in order to replace the variables, I'm going to have to look for a secondary equation, which is going to allow me to get rid of either the x or the y. So what I'm going to do now is think about, the other piece of information I haven't used is this 50 inches squared. I know that that's a rectangle, and I can multiply the x and the y, and that should give me 50. I'm going to choose to solve for y, although solving for x is equally as easy, but just for the sake of, I don't know, we usually use x, or because x is the variable on your calculator, I guess that could be a reason. I'm going to divide by x, and I'm going to get that y is going to equal 50 over x. So wherever I see a y, I'm going to replace that with 50 over x. So it comes out to x plus 4 times 50 over x plus 8. Now, if I was going to do the derivative of this by hand, I would distribute everything, and I would end up with something that's not that bad to differentiate. But remember, you can use your graphing calculator to graph this in y1, and then in y2, you can take the derivative of y1 when x equals x. And that will help you find the critical point by setting that derivative equal to 0. Okay. Feasible domain. Well, let's talk about the feasible domain. What could it be? We're dealing with x, so the smallest possible value of x would be 0. You can make it nothing, and then y would have to be really, really long. It'd have to be 50. But in that case, there really wouldn't be much area. So we know that's not going to be the answer. So what's the biggest x could be? Well, we could stretch x. We could continue to make x bigger, and as x gets bigger, y gets smaller. Eventually, y disappears, and x would be the entire length of the 50 inches. So our answer is going to be somewhere between 0 and 50. So you can use that if you want to kind of change the window in your calculator so it's a little bit easier to follow. Once you do that, you set your derivative equal to 0. You identify that critical point. I think I worked this out and I got that x was equal to 5. I actually worked it out by hand, but you should get 5. And so x is equal to 5. That's just your critical point. You still have to make sure you test it. Again, if you look at the graph of a prime, you should get a, since we're minimizing, you should get a negative, which means going down, and then a positive, which means going up. So you should get something like that, which would prove that x is your minimum. And again, you just look at the sign of the derivative, or the location of the derivative. And then finally, let's give our answer. It says, what dimensions will minimize the amount of paper used? Dimensions are the dimensions of the overall poster. So if x is 5, we can say that we're going to have a 9, and this is inches, yes, 9-inch by 5 plus 8, which is going to give us, no, sorry, y plus 8. I first have to find y. So I'm going to do 50 divided by x, which is 5. And that gives me 10, and then I'm going to add my 8. And so, of course, the y then becomes 18 inches. So the dimensions that will give me the most, the least amount of paper usage would be 9-inch by 18-inch. And that's your poster example. Hope it made sense.